And actually, I do think that you see more predictions on count data than you may realize, because every single time you go to a supermarket, there's some kind of prediction on count data underlying that, but I'll go into that in a second. Okay, so thank you very much for the introduction. Thank you everybody for being here, for actually coming to my talk. I hope you'll stay until the end. So my context today is predicting large numbers of low count numerical target values. So prediction of classification, prediction count values, large numbers of those, possibly grouped, it's in parentheses, so it's not absolutely necessary. And of course, this is motivated from where I come from. Retail sales at a store times stock keeping unit times day granularity, very low granularity, and you need that for replenishment. So you need to know how much you're going to sell tomorrow because there's a promotion coming up. You need to know that in the store today so you can order. It's a little too late. You can find out later on, after tomorrow, that you've sold a lot of products if you ran out of stock and your customers left the store without purchasing anything. So that's where you need it. And there's lots of other applications too. So I've seen some people around here from insurance companies. So if you're predicting insurance claim counts for a single person, you hope that there'll be a low count involved. Not a high count, but a low count over a year or something like that. And perhaps you want to group that by geography, by sex, by zip code, by anything else, by socioeconomic status, stuff like that, or any other number of occurrences that are pretty rare event occurrences. It could be in the time series forecasting context where I come from, or it could be somewhere else. So the question is, how do we assess whether such a prediction or forecast of that is any good? The first thing that comes to mind for people that in forecasting is to look at point forecast accuracy measures like these here. There's a mean squared error, MSE, that just says, okay, we have a realization yi and a forecast or a prediction yi hat. We take the square of the difference, sum it up, and divide by the number of occurrences that we have here. That's the mean squared error. And then we have the mean absolute error, which does essentially the same. It just doesn't have the square term up here. It just takes the absolute number here, so mean absolute error. We can also do something like percentages, so you divide by the actual. Or you can do something like this here, take the sum of the absolute deviations and divide it by the sum of the actuals. And this turns out to be a weighted mean absolute percentage error. Or a mean absolute scale error, which is pretty common in the forecasting literature, maybe not so much common outside the forecasting people. Okay, and now, before everybody goes to sleep, I want you to do some work. Who has the event app installed on his smartphone? Wonderful, lots of people. So please pull up your app, go to the agenda, tap on the top left, there's the menu, go to the agenda, select this talk, and then you see Befragungen, top right, as a tab, and you go there and you vote for your favorite point forecast accuracy measure. And I'll show you if this works out. Here we go. So, waiting. I'm waiting. Oh, wonderful. Things are happening. First vote, second vote. Wonderful. I was kind of afraid that everybody would just say, I don't do numerical predictions, in which case I would have asked you, why did you come to this talk for? Right, okay. 3 votes. Everybody takes mean squared error. Oh, we do have some made people here. One made person. I'm not going to ask who's the made person. Okay. Anybody else? 5 votes? Okay, wonderful, wonderful. 6 votes. It's coming along. Okay, wonderful. So these are essentially the kinds of error measures that you see in forecasting, and Stephan Kolassa knows all about this here, and lots of other people also know a lot about this here. And I'm going to talk a little about these point forecast accuracy measurements and about other things. So I may be preaching to the choir here if everybody uses mean squared error, which is wonderful. Okay, perhaps you can look at this a little later on. Let's just continue for now. Okay, so all these wonderful error measures have advantages and disadvantages, and I'm not going to go in deep detail through all these different advantages and disadvantages. One thing here for the mean squared error is if you look at time series, and you have many time series from many different, for instance, products that sell in a store. You have fast-moving products, slow-moving products, and if you want to compare the mean squared error between a fast-moving and a slow-moving product, then you're kind of out of luck, because a mean squared error of 10 can be very good for milk, which is a very fast-moving item, and it can be terrible for a particular type of shampoo, which is a very slow-moving product. So in cases like that, you're kind of course, use something like a percentage error, any kind that is more or less comparable, but that has different problems here. It's also more intuitive, so once you talk to non-data scientists, the managers that actually sign your paycheck, they understand percentages rather well. They don't really understand squared bottles of shampoo and stuff like that. So the mean squared error has its advantages, but it also has its disadvantages. And it turns out that optimizing on some of these point forecast accuracy measures can lead to systematically biased predictions, especially in our low volume count data situation here. And it's better to predict and assess full densities, full predicted densities, and that's what I'm going to make little advertisements for here. Actually, this is going to be my first part, how mean absolute error and stuff like that can lead you to predict and to biased predictions. And the second part will be how to assess full predictive discrete densities. There's a full paper on this that's recently been published. Okay, let's go into part one. Optimizing certain point forecast accuracy measures can lead to biased predictions. May not be new to you. It was new to a lot of forecasters, I think, looking at the literature. If you have any probability distribution, any distribution whatsoever, if you want to summarize that by a single functional of the distribution, there's different ways you can do that. You can summarize a probability distribution by its mean, for instance. And then that's part of what you learn in your statistics classes. The mean, the expectation of a probability distribution, minimizes the expected squared error. So just integrate over the error, and the squared error, you get the minimum if you predict the mean. And if you take the median, that one minimizes a different function. It minimizes the expected absolute error. And that's usually not taught in introductory statistics courses, although there's a very, very nice visualization of why that is so. It's a wonderful paper in the American Statistician, very recommended. So if we translate that into forecasting, predicting, if you have an idea about your future distribution, if you assume your future distribution will be Poisson distributed with a mean of 0.5 or something like that, if that's what you assume your future sales, claim counts, whatever to be, then if your bonus depends on minimizing the MSE, you predict the mean, predict 0.5. If your bonus depends on minimizing the expected mean absolute error or mean absolute deviation, you don't predict the expectation, you predict the median. That can be a very different thing for count data, which are usually asymmetric. Or turning it around, if you optimize your forecast method or your parameters or whatever it is to minimize the mean absolute error, and the future distribution is skewed and not symmetric, then your forecast will be biased. You will systematically under or over forecast. And this actually looks rather trivial, essentially is, but I looked at lots of papers about intermittent demand forecasting. There's lots of people who work on that, and most of them were very surprised that the very best method for forecasting intermittent demand was a flat zero forecast. So that was exactly what's happening here, because they were operationalizing best in terms of MAE, whereas some other error measure that was simply optimized by the median, and the median for an intermittent demand time series is often zero. If more than half of your realizations is zero, then the median of your future expectation of the future distribution is zero, assuming stationarity. And then so the zero forecast was the best, and people had to bend over backwards to justify why they still like their favorite method better than the zero flatline forecast. Well, I understand why you'd rather have a non-zero forecast, but it just didn't work with their MAE. Yeah, that also applies to lots of other error measures like this scale error or the weighted MAE, which are simply scalar multiples of the MAE. And just a little example here. If you have a Poisson time series or a count or whatever in the future and you want to forecast something that is distributed like this here, is just a simulated realization of a Poisson 0.5 process or a Poisson 0.3 process that can look like this here, or a Poisson 0.6 process or something like that. In each of these cases, if you want to minimize the expected mean absolute error, you forecast a flat zero. If you want to forecast to minimize the expected mean squared error, you forecast the expectation, of course. So, and of course, I'd say that for something like this, a flat zero forecast probably doesn't make a lot of sense. And very much then, this really has kind of implications for how to set the performance measures for forecasters. So that are not used in AE if you have intermittent demands. Okay, we're moving on to part 2 now. We've seen that point forecasts are not always useful. Here's another example. These are just 3 different time series simulated. All of them have the same expectation of 2. The middle one is a Poisson. This one is a negative binomial, and that one is a binomial, so non-negative binomial. In each case, the mean would be a 2, which is wonderful. So your point forecast, if you want to go for a point forecast, you'd forecast 2. If you want an unbiased forecast, that's wonderful. But then, well, you look at things here and you say, okay, a point forecast is 2, that's the optimal point forecast under squared loss, that's wonderful, but does that help me? So if this here is your future sales in your supermarket or whatever else, a forecast of 2 is wonderful, but most actual demands are far lower, and there's demands that go up to 18 or something like that. So how much does that have to do with a flat line of 2? And it's more importantly, it's wildly different from here, where all the realizations are 3 or lower. So does a point forecast really help us? It doesn't help us for setting safety amounts, for scenario planning, for any kind of sensitivity analysis or stuff like that. So for anything, I would argue that for most uses, for most use cases that actually consume a forecast, you shouldn't aim for a point forecast, or a point forecast in a measure of variance, which is better, but still not good enough. I'd say we need to forecast a full predictive density. We need to forecast a full future density, and when we forecast it, it's a predictive density. Wonderful. Okay, so that's what we want to do. How do we assess whether what we're doing is good or not? We have a predictive density. We want to forecast. We say, okay, this year we forecast a Poisson distribution with a correct parameter. How do we find out that that's actually the correct density? And if we forecast a Poisson distribution for this person here, for this time series, how do we find out that that is actually not correct? There's a couple of tools that have been developed for this. And I'm actually not talking about lots of very new things here. This is a probability integral transformation, the PIT. That's not my brainchild. That's been used for a long time in finance and macroeconomics, where people have routinely forecasted full predictive distributions, usually normal distributions. Then they found out the hard way that the normal distribution doesn't really work because it's real financial returns are fat-tailed, and so after a crash a couple of years back, the fat-tailed distributions became a little more en vogue. How does this work? Well, suppose we have some kind of future density, forecasted density ft, so at a time t, or it could be, if it's not time ordered, if it's just ordered, then we could have an fi, it doesn't matter. And a cumulative distribution function f hat t, capital F hat t. So this covers the case that you might have different distributions for different times, points in time. Then you just take the actual observation that belongs to this time point as follows. Well, it's a simple distribution, it's a simple transformation. You just take your predicted probability that your actual realization would be lower than the realization you actually saw. Well, that's a fancy way of saying you just evaluate the cumulative distribution function, the forecasted CDF, at this point. And this is yet another variant of writing this. Why? Well, if you think about this a little and think back to your introductory statistics classes, that means that if you actually have the correct distribution function for the future, if your predicted density is the correct density, then these PTs here will be uniformly distributed between 0 and 1, because that's just a reformulation of the definition of the CDF hat. And then, well, you have lots of P's here. As I said, you have large numbers of realizations. And you want to see whether these are uniformly distributed. Well, you can test them. There's lots of literature on testing uniformity. Often people do the roundabout way and transform it into a normal distribution, then test normal distribution. I don't like that. But it doesn't matter. There's different ways of doing this. So for instance, if we have a log normal distribution like this here, there's the density just turns sideways for the log normal distribution. There's just 500 realizations. You see how they're skewed. And if we run through this process here, and in each case have a predictive density that is log normal and correctly specified, and run through and get this PIT here, this probability integral transform, then you get a histogram, and that is reasonably uniform. It can be uniformer if you get more samples. That's wonderful, right? wonderful. It's so wonderful that it's been used for 20 years, something like that, in the finance literature. Everybody there uses this. It's wonderful. Much less used in supply chain or other forecasting approaches. And why? Well, we have one problem with discrete predictive distributions. So if we have a discrete predictive distribution, there's just a simple Poisson down here, okay? And there's the realizations, and that's the kind of demands you might observe in the supermarket, lots of zeros, and you might observe 1s and 2s and sometimes a 10, but you don't observe sales of 2.3 bottles of shampoo, nor do you observe sales of minus 1.7 whatever else. So you see these predictive distributions. If we run through the same exercise here, we have to correct future density. If we have them correct, if we actually do have Poisson distributed sales, and we know that we have Poisson distributed sales, and we run through this here, well, what will come out? Well, there's only a discrete set of PTs that can happen. Right? If we see a 0, then the PT is just the probability of observing a 0 in this Poisson distribution. That's just a number, one number. If we see a 1, the PT is a probability of observing less than 1, or one or fewer units. If we see 2, and so on and so forth, it's just the PTs in a stationary distribution will be discrete. They will certainly not be uniform, right? So all our wonderful theory here of getting a uniform histogram of PTs, it doesn't work anymore. We get something like this here. This is the P, this is a transformation. This transformation for the correctly specified distribution, and it's anything but uniform. So this doesn't work in the discrete case. Okay, so what do we do? Well, fortunately, there's a smart idea. I can call that a smart idea because it's not my idea. Actually, it was my idea, and I was completely, I was amazed that someone like this, wonderful, nice, wonderful idea, wrote up a manuscript, circulated it, lots of other people found it wonderful, and then one person, Tilman Kneiting, wrote back that he found it a wonderful idea, and it was so wonderful that at least 3 other people had independently found it before. It looks like every 10 years somebody rediscovers the same thing, right? And I just came along in 2015, so it's like a quadratic cycle, right? Of the randomized pit. Well, the idea is very simple. If we observe a 0 in our sales, and we know in our Poisson predictive distribution that the probability for a 0 is whatever, say 0.9, then we don't just write down a 0.9, and we draw a random number between 0 and 0.9. If we observe a 1, then the probability for a 1 in our predictive distribution, in our Poisson, maybe 0.95, then I just draw a uniform PT between 0.9 and 0.95, and so on. It's just a randomization of the pit. And that takes care of smearing out this big bump to everything over there, and smearing out this bump to everything over there, and so on and so forth. And again, it's the same thinking. If we have the correct future predictive distribution, then again, these randomized pit will lead to a PT that is uniform on 0, 1. Again, we can start testing. Okay, so here's a little example here. There's a Poisson distribution on the left and a negative distribution on the right. They both have a mean of 0.4. So that means that the point forecast minimizing the MAE would again be 0. So it's a classical case where this problem would occur. And then we have 2 different hypotheses. One is correct. We hypothesize a Poisson 0.4. That works for this one. Doesn't work for this one. Or we have a hypothesis that these are McBin 0.4, 0.2. That works for this one. Doesn't work for that one. And these are just the randomized P's that we get out of this here. This here, correctly specified Poisson distribution, all essentially uniform. PTs, correctly specified McBin, essentially uniform PTs. Wonderful. And if we assume that our McBin is going to be Poisson distributed, so we have a misspecified future density, then we get something like this, which has a big hole here, and then it bumps up again here, so this is really not uniformly distributed. And if we assume that our true Poisson is negative binomial distributed, then we get something like this and a sharp peak up here. And then we can run any kind of statistical tests, and I just took some smooth tests for uniformity, data-driven, Pichek and Levina. You see a test statistic, WT, and a p-value for the test statistic. And there you see we can reject normal uniformity in these two cases, and we don't reject it here. So it does seem to work. Okay, wonderful. And how do we apply this to group data? That is multiple time series. For instance, or claims counts that are grouped by geography, by zip code, by something else. Well, there's different ways and simple ways here. One possibility would be take all the p-values out of this randomized pit for all the different time series, for all groups, for all entries in all groups. And then we have one giant vector of p's, and then we can test that one for uniformity and start visualizing. Or take each groups, each series p-values, test them for uniformity. Then we get a test statistic for each series, and then we can start plotting and summarizing and comparing these. Both are possible ways of going about this, and adding and giving some information about what works and what doesn't work. So here's a little illustration of this with two data sets. And as I said, I come from retail forecasters. So I took two data sets with daily sales, one supermarket each from two different European retailers, to 1,000 series each, and forecasted up to 100 days ahead for each series. And I tried different forecasting approaches, and I used some from the 80s, right? So not the 50s and 60s that we just heard about. Actually, this is homegrown. This is a very simple idea. Well, the point is here, we need density forecasts, and the problem is, of course, that many of these standard forecasting techniques, exponential smoothing, don't really necessarily have an underlying statistical model. Well, they mostly do, but it's usually not implemented, so it's hard to get something that actually works, gives us a density forecast for discrete data. There are integer autoregressive models that may or may not work, but are not very common. I just went with some very simple approaches. There's empirical plus weekday. I call this. It's just, we have a density, we want a density forecast for next Friday's sales. Well, just take all historical Fridays and look at their sales, and look at their distribution, and that's the density, that's a probability mass function for the next Friday. Same for next Saturday, same for next Monday. Empirical in terms of it's completely non-model based. It just takes the corresponding weekday and looks at what we've observed empirically. Another forecasting approach would be Poisson regression or negative regression, because these, well, yeah, including day of week, price, trend, Christmas, because we know that these have an impact here. Yes, it does have a linear impact on price that goes through the link function, so it gets turned non-linear in between. And these give us density forecasts. Of course, once you start including parameter uncertainty, the true forecast, the true density would not be Poisson anymore, it would be over-dispersed. But I didn't look at that in this context. I did look at in the paper I looked at many other approaches, for instance, bootstrapping these to account for the over-dispersion that comes from parameters in uncertainty. So it just doesn't make a lot of difference. And these are the results then. Retailer A, retailer B. At the top, we see histograms of these R-pit p-values for empirical plus weekdays, for Poisson regression, for Mecklen regression, the same on the right for the other retailer. Let's start with that here. What do we see here? Well, let's look at Poisson regression first. We see a histogram that's kind of U-shaped. We see, and the flat line, that's where uniformity should appear, right? Anything that's close to the flat line is uniform, and that's wonderful. And this is not close to uniform, that is not wonderful. Now we see lots of p-values here to the left, and very many p-values at the very right. What does that mean? That means that we have seen many sales that are far below what we expect. They're very low compared to what we expect. So the left end of our predictive distribution is overrepresented, and similarly, the right end of our predictive distribution is overrepresented in the actuals. What does that mean? Well, it doesn't capture, Poisson regression doesn't capture the overdispersion. More low sales and more high sales than we expect, given our Poisson assumption. So Poisson assumption doesn't make sense for these supermarket sales here, and it's the very same picture for retailer B. So these are two completely different retailers. One is a drugstore, the other one is a grocery. So, and in either case, it doesn't make sense to use a Poisson regression. The empirical plus weekdays and neckpin regression, they perform better. Neckpin over here and plus empirical over here still have a hump at the very low levels. They both have humps at the high levels here, right? But at least for this retail here, we've captured with the empirical plus weekdays or the neckpin, we've captured the low levels, the low end rather well. And we always underestimate the incidence of the very high sales for any of these here, right? The probability for high sales is always under forecast. And we see that in this randomized pit here. And down here, well, I subjected each time series to this data-driven smooth test and then just plotted the WT test statistics, and you see how the test statistics lower is better for empirical plus weekdays, and neckpin regression are lower than for Poisson regression. And this is actually quite a difference here because of the logarithmic scale. And that just, again, reinforces that Poisson regression doesn't really make a lot of sense. Yeah, as I said in the paper, I looked at about 15 different approaches. So I originally looked at 13, then one reviewer suggested adding another 2, so I kind of know who that reviewer was. I added them, they didn't perform rather well. And the summary really is that this empirical plus weekday set doesn't even include prices and stuff like that, or seasonality or anything else, just the day of week, but that is incredibly good and incredibly hard to beat. So yes, smart new technologies from the 2000s and 2010s and non-linearities may be useful, but to a degree, very simple approaches, very easy approaches might be actually work rather well. Okay, and actually, I'm well in time. That's a conclusion. My conclusion is, don't rely on the mean absolute error and similar things to get an unbiased point forecast, especially if you have count time series or anything else where you expect large values and small values to be differentially represented. If you have asymmetric data, don't look at the MAE. If you do need to report them, mean absolute error, MAPEs, percentage errors, and to sometimes have to report them because people want to know them, because people, as I said, are more comfortable with the weighted MAPE. Well, then at least also report whether you have bias. If you have a point prediction, it's probably better to use MSE, which many here are using, whether root mean squared error or a scaled version or something else. But I would argue it's better to forecast full predictive densities and then assess them in some way, as we did here, for instance. And there's an alternative to the RKit, and that's also the other part of the paper, which is proper scoring rules. Scoring rule, I have a lot of time left. I actually have to slide on these, but I'm not going to do that to you. A scoring rule, the idea is it's a function that takes a predictive density and a realization and maps these to a score. And you do that for many realizations and their corresponding predictive densities. You get many scores, and you average them. And the proper scoring rule is one that is minimizing expectation if your predictive density is correct. And there's a couple of these that have been developed. They're more common again in the continuous context, but there are some of these that actually work for the discrete context. So you can use these. And they paint actually the same picture than as we saw here in the paper. They just don't show these wonderful histograms up here, and these are actually easier to interpret and easier to understand. So that's why I didn't talk about the proper scoring rules, although they are slightly more sophisticated, but then again, slightly harder to understand. And of course, the problem here is all of these, both proper scoring rules and the RKit, they only look at marginals, right? They don't look at any correlations between errors. And if we're looking at daily data here, it's immediate to think about, do we have a problem here with remaining weekday patterns here? If we have seasonality and if something goes up, then we should see some kind of remaining seasonality on a lag of 7 or something like that. Well, that would be also something you could look at. And there's a couple of papers that do something similar, again, in the non-discrete case, by doing Markov chain alternatives and seeing how the errors compare with them, whether there's remaining autoregressive or other structures. That is extremely hard for low counts because there's simply very low power involved here. If in a drugstore, for a typical product, you sell 1 per day, perhaps or even lower, then whether you sell 2 on 2 consecutive Saturdays doesn't really mean a lot. There's just a lot of sampling variation in there. So it's extremely hard to do that for low counts. There's very low power involved here. And finally, I'd say that full predictive densities are important, and probably more important than point forecasts. The problem is most people only understand point forecasts, and that's what they understand as the forecast. I'd say the forecast should be a full predictive density. But finally, what you should really do is assess the consequences of your forecast. So here you have a point forecast or a predictive density or whatever. It's not the end of the story. You take the forecast and prediction, you do something with that. If you do credit scoring, well, you do something with that. You give the guy a loan or you don't. And then you should really look at, well, did that perform well? Is my profit going up or down? And in supermarket sales forecasting, the question is, how much stock do I have and how much out of stocks do I have? Stuff like that. So you should really look at the consequences of the forecast, cost of forecast error or forecast value added, or just some tags that you can find in the literature on this here. And these will usually include interval forecasts for predictive densities, because you need some kind of safety allowance often, and subsequent processes like logistic optimization for replenishment. And just a little answer to Sven's talk, last talk here, why do people keep on using simple methods? I've often seen in my experience that smarter methods, newer methods may be more accurate, but once you look at the subsequent processes, for instance in supermarket retailing and supermarket forecasting replenishment, if you have sales of 4 tomorrow and you have a forecast of 6 and a forecast of 5, and of course the forecast of 5 is more accurate, wonderful. But if you can only push product into the store in multiples of 8, because that's a logistical unit, then it doesn't make much of a difference whether I use a smart method that has a forecast of 5 or a dumb unit that has a forecast of 6, or even a dumbest unit forecast that has a forecast of 1 unit. And that's something that I see often, and that may, with agile supply chains, change in the future, which makes it even more important to actually look at not only the forecast, but at the consequences of the forecast. And I see that I only have 5 minutes left, so no, I'm not going to read to you the entire Okay, I couldn't resist to plug my book. Just came out a month ago, Demand Forecasting for Managers. So if you work for somebody and do forecasting for him and he doesn't understand forecasting, give him this book. It's inexpensive, it's easy to, I always like to say it's less expensive than a good bottle of wine. It reads about as quickly as a good bottle of wine is consumed, and it doesn't give you a headache afterwards. So there's flyers outside. Thank you very much.